So I'm going to start talking now if everyone's ready. Okay, so today, I'm going to talk today about coronal mass ejections this morning, and then the interplanetary components later in the afternoon. What I'm going to try to do is a flavor of what I am aiming to do at least, is to give you as many concepts as possible without trying to overload you with too much details and theory. And my motivation behind this is when I was a summer student with you guys, one of the greatest strengths I liked about this summer school was the breadth of the information that was given to me. And in such an area where it's so interdisciplinary, I think if you want to attack some big problems in science, you want to know as many tools are available in areas outside your general research area. And that helps you collaborate with other people and attack a problem that you would think is necessarily possible. And so under that idea, you want to know what's available to do, or what tools that you have available to you to use, and what observational characteristics or simulations are possible in its current form. So under that, that's what I'm going to try to do, which means it'll be very overview for each individual component. So for those of you that actually research this area, it might be a bit too overview, but hopefully it'll be a good broad breadth. And you'll have the presentation slides for the rest of the time, so you've got somewhere to go back, and I've put lots of references in, so you can always go back and read out more of the details. So I'm going to first start. We haven't really done too much on what a CME is. So I've just shown this as a movie, and so actually that was very quick. I'm going to try going back again. The CME just got launched right from the center, right at the beginning on the Okay, I'll give up on that. It launched, it went from the inner image, and then this is core 1, and you saw core 2. And so what you're going to do again is you're going to see our SDO type image, where we're seeing the launches of a CME, so effectively the destabilization. And then feeding it through all the different cameras and all the observations that we have to highlight how we actually can get better characteristics of what we're seeing. What's interesting here is you're seeing all these streaks going through the camera, and that's from the SEPs hitting the detector. And so you can see the CME launching, and then you quickly get problems with your cameras as the SEPs arrive. So the general structure I'm trying to go through today will go under 3 main themes. Firstly, the problem of how we initiate the CME. I'm not going to go too much into the destabilization, and all the instabilities, which Amitava did earlier. But I'll give you some motivation of the models that we use trying to create these. Then we'll just go into an idea of, okay, let's ignore the complexity of how we initiate the problem. Let's just say we do have some sort of helical magnetic structure called the flux Ro, and call that the CME, and put it into a simulation in an already unstable state, and see what kind of understandings that we can get from that. And then thirdly, I'll finish off with all the sort of possibilities of what we can observe and what characteristics we can pull from our cameras and our data. And what I want to highlight here is there is a lot of conflicting theories and observations. People have lots of strong opinions, and you'll know that when you go to conferences, and people will give you, they will tell you that they know everything, and it's down to probably their model or some of the observation they've seen. But hopefully with this presentation, I want to show you that there are conflicting ideas. And I think that's what you should be able to take away from here, is that if you think there's only one initiation idea, that's not true. There are multiple, and they all have strengths and weaknesses. And so you should kind of come away from here a little bit confused in that you're not entirely sure how to initiate CME or what we're actually observing. Oh, and by the way, please ask questions if there's anything. Okay, so we'll start with some of the sort of characteristics of initiating. So I've called this the chicken or the egg problem, but let's just first start with what are the general characteristics, some actual numbers, so we have a handle on what we're actually seeing in the Earth, and at the Sun. And what we're kind of having a look at is the energy sources at the Sun in terms of the kinetic energy, the thermal energy, gravitational, and the magnetic. And what you're seeing is the actual energy densities in the magnetic characteristics are much higher than everything else, and it's high enough for your destabilization and for the characteristics you see for CMEs. So a lot of what we'll talk about will be focusing on the magnetic characteristics. And what I wanted to show, because I couldn't put this into my, actual presentation, so I wanted to show you this as a movie. And the reason is because NASA actually provides some of the best visualizations. In fact, this doesn't have audio, does it? So I'm going to try connecting my Bluetooth. So sorry about this. I'm going to pull that out. For some reason it's not connecting. I checked this early this morning. Sorry about this. It's connecting to my phone, that's why. This doesn't work, I'll just speak over it. Okay, I'm going to give up on that. I'll try to put the speakers onto my laptop as high as possible, and we'll try to go from there.
Clouds of plasma and magnetic field occasionally scientists study them because the massive bursts pose a threat to space-based technology and even power grids on the ground. Coronal, known as a flux ro, tightly wound groups of magnetic field the sun itself. New research using NASA's Solar Dynamics Observatory has now shown that they can be seen in just one of its cameras, which shows the very hottest material on the sun. By watching a flux rope form and eject as a CME, the research has brought some closure to one long-standing mystery, whether ropes form before or during the CME's eruption. It's impossible to actually see the flux ropes, or any of the sun's powerful magnetic fields involved with CMEs and flares, because these fields are invisible. But scientists can map them by observing plasma trapped by these fields, which shows up as thin lines in extreme ultraviolet light. Since Earth's atmosphere naturally filters this UV light, scientists must observe it using telescopes in space, such as NASA's SDO, so there have been relatively few detailed observations of CMEs, particularly at higher temperatures. SDO images the sun at high image and time resolution. It is also the first satellite to consistently observe light with a wavelength of 131 angstroms, which highlights plasma at temperatures of around 10 million degrees. This wavelength is usually reserved for studying solar flares, but what NASA and Naval Research Laboratory scientists found is that the flux ropes associated with CMEs could only be seen at this temperature. On July 19, 2012, a CME erupted from the visible edge, or limb, of the Sun. Because it was on the limb, the flux ropes were in profile and particularly visible. Even more important, the flux...
So this is the point I wanted to actually highlight, which is a recent observation trying to show the idea that what I was talking about is the chicken and the egg problem, which is, does the flux rope type structure start before the flaring and before the CME exists, or is it the other way around? And this is one example where they've recently found that the flux rope was present before the eruption. And this is this variant is more difficult to see. And so that's what this is about. So hopefully you'll see that again.
Ropes appeared about 7 hours earlier in the same location. The ropes were visible as a line of figure eights that looked exactly the way theorists predicted they would. This is the first direct evidence that flux ropes form well before a coronal mass ejection. Footage of the CME from the SOHO spacecraft confirmed the presence of the flux ropes. By adding footage from the Stereo A spacecraft, which is viewing the Sun from an entirely different angle, the researchers were able to create a three-dimensional picture of the flux ropes. For the most part, they follow the classic figure-8 pattern previously observed and predicted by solar models. But some of these ropes also had feet which extended farther away than scientists expected. This deviation from the models is interesting and requires further study. Besides showing proof of early flux rope formation, this study also paves the way for future flux rope and CME research by literally finding a new light to observe them in. The possibility of using flux rope formation as an early warning system for CMEs means that this line of research can have some very practical and far-reaching applications. And it can also help wrap up some of the long-standing mysteries of the Sun.
Okay, so that hopefully gives you some idea of the motivation behind what we're doing, as well as the characteristics of what we're trying to observe. Back. Okay, perfect. So this is, while this was one movie that was showing the structure forming with the CME structure starting first, there are two variants of how these objects erupt. And so it's the idea is, does the reconnection that we start with lead to instability that then creates the eruption of the CME structure? Or is it the instability of already pre-existing CME structure that then leads to further reconnection of the overlying field, and then you get the eruption? So it's a question of which way around do you think these are happening? And scientists have been going around trying to figure out which one, and I guess in many senses, what the probabilities of both. And what I showed with the movie earlier was one example of the CME flux rope pre-existing before the eruption. That's a much more difficult problem to observe, and what has been observed more frequently over the last decade or so is the other version, which is you've got this arcade before the CME. And so you see the arcade, then you see reconnection, then you see the CME forming, or the flux rope forming. We can go over that. So this is, again, I'm just going to quickly go over this. It's an idea of what is the causality and what is the formation. And so there's some uncertainty about how the CME gets erupted. And so I'm going to be talking about, effectively, this top section, which is this release of magnetic fields out into the heliosphere. And it happens when you get these loops, flare loops, that destabilize, create a current sheet, and then the top section effectively is our CME that we launch out. This bottom section is what will be talked about tomorrow in the lecture on flares. So this is something I'm not going to dwell on too much, but more for you guys to have in the literature, something to hand. And this is all the different methodologies for creating an eruption that I could find. in the literature. And there's many different ways of creating this CME and erupting it and getting it to destabilize into the heliosphere. And these are some of them. And I'm clearly not going to be able to go through all of them, but it is useful for you to have just to get an idea. And if you ever want to get into under the hood to understand which ones each, what each are doing. So I'm going to go into two general sort of topological type approaches. And that's what we were talking about earlier, which was, does the CME start first or second, depending on when you think of it. And so first you can sort of think about it as a shared arcade of fields. And then you destabilize it and create a flux rope, or you start with a twisted flux rope. And I want to take a quick break for a second, because I just realized we didn't really go into flux ropes, Bessel functions, or anything this week, have we? Have we? Okay, so I've jumped the gun somewhat. Okay, so what a flux rope is a helical structure of magnetic field that is much like, if you can picture the DNA in a helical structure, that's an object that we're looking at. That's what we call a flux rope. So it twists on the outside circle of this cylinder, it twists a lot. And as you get closer to the center, the central axis, it becomes more of a straight line. So it's this object that's magnetic in structure that we call a flux rope. And that is an object that constitutes predominantly the majority of people's mental picture of what a CME is. And obviously there's plasmas and there's lots of other characteristics, but that is a general idea that people think about. And so one simple solution for this helical structure that is a flux rope can be created out of something called Bessel function, and it's a mathematical analytical solution. So I apologize for not including the theory behind that here, but that's what I would like you to have as a mental picture moving forward. Of when I interchange between the words flux rope and CME, it's predominantly the same. Is everyone okay with that definition of a flux rope? A yes or a thumbs up would be great. Okay, perfect. Okay, so in both these scenarios, you can actually have a strong shear component, and what destabilizes this is how they define the amount of twist. And that's critical for many of these initiation problems. So if we focus on the sheared arcade first, there's three kind of general concepts that I'm going to focus on today. And that's the tether cutting model, the breakout model, and generally we're going to talk about the shearing parameter space. This is an image I wanted to show. So this is, okay, the resolution on this isn't terribly good. If I maybe, that's a bit better. Okay, so when I talked about the shearing arcade, this is what I was trying to highlight, is you get these loops that come from 2 foot points, and you've got field line that come out of one, turn into an arch, and come down to the other. And that's an arcade of field lines. And then when the people talk sheared arcades, that's just taking these 2 foot points and moving them a bit. And so now it's not perpendicular over this hypothetical polarity inversion line. It's kind of sheared. Let me take a step back. Polarity inversion line. If you've got a positive section on one side, a negative section on another side, and you've got field lines that are connecting the two in terms of loops, on the surface where you've got positive and negative, there has to be a point somewhere where it turns to 0 from positive to negative. And that creates, if you're talking about surface problem, you've got a surface that's positive, a surface that's negative. That creates a line that's neutral, and that's called the polarity inversion line. And so these arcades are things that cross over the polarity inversion line. And if you move these foot points and shear them against each other, they become sheared arcades. So out of these two of these mechanisms for CMEs, the general concept that you want to walk away from is, where does the reconnection occur? And so the breakout model focuses on having magnetic field lines reconnect in an arcade above the CME structure, or above the flux rope. And in this diagram, I didn't put, I'll show you more pictures of it later, but if this is your CME, and this is an overall overarching field line on a macro scale much higher up, then the breakout model is talking about reconnecting field lines above, which means between points at this region. And the tether cutting model is talking about it predominantly about reconnection happening below, and so then that's at this location down here. And in a 2D schematic, that becomes difficult to visualize. In a 3D, you can visualize it, and you can understand how this is actually happening. And so this is an example of the tether cutting happening below, but in 3D. So if you see, what actually happens is these two bits can connect. And that's effectively saying this part of the line is connecting with here, but that's because it's happening because they're not directly aligned on top of each other. So the basic principles of the tether cutting is something goes through some theory and work, and actually it's in the books that you guys have got, in book 2, and this is a figure I grabbed from there. And if you want to go into more of the theory behind that, I'd invite you to go read them. But the idea here is looking at how the CME destabilizes and lifts up above the surface. And this is a focus on creating the flux rope and showing looking at the energy state that occurs from that. And so what you're looking at here is as more field lines reconnect and create a larger flux rope, so effectively starting from this region here and reconnecting more and more, the CME launches and increases in height. And that creates a current sheet behind it and changes the energy state in which you're at to the point where you get to this critical point in terms of energy where there's no more restoring force, as it were, for the CME to remain on the surface, and it just erupts. And that's effectively this section here. So moving on to the breakout style model where the field lines are occurring above the CME structure. This is an example. I'm going to show another movie here. I'm going to start here quickly because this is in color, and I think this now actually shows it a bit better on the screen. So what we're starting here is again, we're focusing on now trying to reconnect the CME above the flux rope. And one of the strategies for that is if you have effectively an octopole, so 4 regions where you've got field lines, and so you have this arcade here in the center, which is effectively going to be your flux rope, and you're reconnecting from this this overarching polar field line, and that reconnects and destabilizes the CME scenario such that it then cannot maintain the CME on the surface, and that destabilizes it. And the way that happens, if we go back, is you start with here, and this X point here is where the field lines from the top section reconnect with this bottom section. That then creates larger magnetic pressure here that's not able to be contained by the lower pressure out here, and it just naturally bursts through. And that creates effectively the flux rope, and then you get natural reconnection occurring at the bottom afterwards, after the fact, and then it can just erupt. So here is lots of blurb of basically what I'm saying, but with the details and the theory, which you can go into afterwards as well. And so this is just an equation I wanted to highlight in terms of the stressing of of the actual field lines that's creating the structure. And so what we're saying here is the initial unstressed potential field in polar coordinates is this, and you've got two main terms. And it's the dipole component that dominates a much larger R. And it's the altipole component that contributes to the more complex regions, which creates the complexities that's happening further closer to the surface. This is a simulation of it occurring that was done a few years ago and performed in 3D. And it's the same idea. And what I wanted to highlight is how the CME can erupt and actually create something that's not so simple as the schematics show. And that is highlighted both in simulations and, more importantly, in observations, where you have this CME structure, but it's very messy as things reconnect. And in fact, what I'll show you later is things can reconnect, rotate, deform, and all manner of things. This is a reconstruction of that same model using a white light rendering of what they think they would have of what they think that CME would have looked like if they had a white light coronagraph. And this is what I didn't mention earlier, which I perhaps should have done, is the general structure of what a CME is, looking at coronagraphs, so the white light images. And that is what's commonly called this three-part structure, which is the CME front, which is bright and a thin band, basically, and often thought of as the leading shock front as the CME erupts. Then you have this dark cavity that contains the bulk of what you're actually observing, and then at the bottom is this core bright section, which is often considered the prominence. So that three-part structure is something that many scientists have had historically as their mental picture and view of what they're thinking of CMEs. That is a very simplistic view that was predominantly driven by chronographic images. With the onset of the stereo mission and being able to triangulate CMEs, as well as looking at CMEs in the heliosphere, this simplistic view is not as simple as we thought. And back then, pre-stereo, in the historical senses, there are a lot of arguments of what is the three-part structure and why. And we've tried to solve many of these in terms of showing that it's simply a projection effect. In terms of sometimes you see the prominent section in the core, sometimes you don't. And this is really down to a 3D object being transposed onto a 2D plane. And so when people start talking about a three-part structure of a CME, that's very much, I would say, an older mentality of what we're trying to think of in terms of a CME. And I wouldn't take too much heart by constantly talking about it as a three-part structure of a CME. More that, depending on which orientation you're seeing different components. So this is just me trying to say, actually, you can have CMEs that are launching with reconnection happening above and below the CMEs, and you'll find in the literature many teams around the world that are trying to prove their model to work, and they'll drive it by reconnecting from above, or they'll drive it from below. And what I'm trying to show here is actually that issue is still ongoing as a debate. It happens. And you'll find cases in observations, in STO, in stereo, where both are happening. And so we really need to start thinking, okay, both can happen at the same time, and perhaps even thinking in a more of a statistical sense, where we shouldn't be thinking that only one strategy works, but what are the probabilities of one works? And that will lead on to the bigger picture of, can we then forecast them? And then, even then, if we have an idea of probabilities, we can then pursue that further into an idea of, okay, if we have a certain probability of one mechanism, can we find out in what are the scenarios that promote those characteristics over another mechanism. And so I think those are the ideas that we want to try to promote moving forward. And so this is an example of that kind of attitude in terms of research approach, which I really liked. And this was done by Professor Kusano recently from Japan, and he was looking at the entire parameter space, basically, of shearing these arcades. Unfortunately, I don't think I have a movie of this, which is a shame because it was actually very pretty if you ever see him. And what he did was use lots of computational simulation time and simulated lots of different scenarios to see when the CME would erupt. And what you've got here is effectively this X line is your polarity inversion line. So you've got negative field on this left and positive on this right. And he's got this field line, these field lines, these arcades that are naturally occurring over this polarity inversion line. And what he does is he injects a small amount he just manually injects a small amount of magnetic flux at an unusual orientation in the center. So in this case, the positive's on the complete opposite side. And so you've got this random, isolated field component that's just kind of going opposite to everything else. And then he looked at this and had a look to see if that actually causes an eruption, if the instability occurs. And he looked at this and he orientated this inversion, this small injection, and he looked at lots of different parameters of the different angles. And so these are all the different scenarios he worked out. And he looked at them very methodically at all the different angles of what he was talking about. His RS is reverse shear, and OP is opposite polarity. And so he looked at all these different orientations of all the different possibilities and tried to find out if it can actually erupt. And so what he's showing here is in this great parameter space is that everything that's shaded is if it erupts. And it erupts more strongly with on the red side. And so this idea of thinking that not one strategy is necessarily correct, but there are multiple strategies, and we just have to figure out the causes of each, I think is an admirable approach, and I think we should start moving forward with that as well. So section 2, after looking at the sheared arcade kind of idea, is the twisted flux models. And so here, I'm going to sort of very briefly talk about three kind of general ideas. A flux cancellation type version, kink instability, and resistive tearing instability. And the instabilities we heard about earlier, and so I'm going to actually skip through most of that. But in these models, an important characteristic that we need to think of what these models have been invoking of what I've seen is that they need to have sufficient twist, and the loss of equilibrium or the ideal instability slips aside or leads to reconnection of the overlying field. And so when I say slips aside, that's an effect of 3D where it can just slip to one side of this CME. Okay. I'll skip over sigmoid formation and the instabilities. I've decided to just skip over the entire sigmoid problem. That's something I will invite you to try to go read in the literature. It's an element that's very important in terms of understanding the instabilities and the causes and initiations of CMEs. But it would require a significant amount of more time. And so what I want you as a takeaway point for what is a sigmoid is think of a letter S and field lines of what we were showing earlier is an arcade, and I was showing a simple cylinder of these field line arcades. Think of the sigmoid as being that cylinder, but now shaped in the shape of an S. And it's that sort of twisting, and then we're talking about sort of the kink instabilities and the other instabilities of how these, once you've got it twisted, it then starts to destabilize. And so there's mechanisms behind that which cause the CMEs, and that's something that is under a lot of active research. Okay, so part 2 of this talk is, let's try to ignore the complexity of how to initiate the CME. Let's pretend that we already know how these things erupt and we don't have any qualms about how it did actually erupt. Let's now think, okay, what are the consequences in the heliosphere or in the upper corona? So in order to do that, that's usually invoked using simulations, and for that we need to have an analytical solution of which we can put into an MHD equation. So we just want an analytical, mathematical answer for what a CME should be, and then just have it naturally unstable in an MHD solution, in a simulation, and let it erupt, and then let's have a look and see if what we create in our simulation is close to observations, and then try to go back in our understanding and look back at our simulations and try to create some insights. Oh, I've got break time here, but I think I'm a bit early. What time am I finishing again, by the way? At 10? Okay. How have I got? Okay, let's take a break here and we'll go from there. Yeah, I've got this. It's great.
Have a break. Have a Kit Kat.
How's that? Okay, guys. So let's start moving on. I think I've left a little bit more than half, so we'll crack on. So the second part of what I wanted to say was looking at some options, analytical models of how we can actually start to get an idea of what we try to get a mathematical idea of what we're seeing in coronographic images. I want to quickly. Nick had a quick word with me. He's sort of misunderstanding a lot of the scale heights of things, and I think I kind of skipped over that, for which I apologize. So I'm going to quickly go back. And let's start here. And I'm going to come here. So I wanted to show this as just a quick movie for the scale. If that launches. There we go. So this is a movie from, there we go. This is a movie from LASCO, and as an idea of scale, what we're showing here, so you guys have an idea of a handle of scale, is the white circle here is now the size of the sun. This is an occulting disk to block out the bright light of the sun, and this is the coronagraph. And on this coronagraph, this is about 30 solar radii away to the outside edge of the field of view. And so these are the images that we've had for multiple decades that we've always tried to understand CMEs from. And this is post or after all these initiation problems that we're talking about. That's happened long before this stage here. So this is the stage I'm now going to talk about, which is, let's say we've got this flux rope. Can we understand why it's that shape and why it has those characters? But the size at which the instability is happening at more of these levels. And so all these instigation models I was showing is actually zooming in more and more right into the sun, and basically at this level. And so this is the height and the sizes of what I was talking about right from the beginning, which is the whole initiation problem. So we've moved out further out once the CME is effectively formed. Okay. So in summary, let's avoid the mechanism of CME initiation. There's lots of them. Let's just assume that we know what's happening. What insights can we now get, just assuming that the initiation problem is fine? And so what we can go with is looking at it from different perspectives. You've got injection of a flux rope into a simulation model. And usually that begins with a general steady state model in 3D of the corona and the solar wind. And so it's in a steady state, and then you just inject some answer that you think is a CME or a flux rope. And so that you just add it in. And usually, not always, but usually this flux rope that you just added in is not in equilibrium, and it will just naturally want to erupt. Or rather, you've added it in with an initial velocity, so it's already just going into the heliosphere. And the object of this is not to investigate the initiation characteristics, but to see how do these CMEs evolve as they move into the heliosphere, and see if your results are similar to what we observe in the coronagraphs. However, solving much of this in 3D is extremely difficult, and so there's been lots of studies of doing this. An example, and so quite often you'll see in the literature, many people start with a much simpler solution, which is what they call a 2.5D analytical solution. And what I mean by 2.5D, which is kind of somewhat counterintuitive, is that it's basically two-dimensional, but in the third dimension, it's all symmetric. So the equations that you use are still fully 3D, so you still have BZ, BX, and BY, BX, BY, and BZ. So you still have all three components in your equations and in your simulations, but one of the directions is all symmetric. So in fact, if you take a 2D cut of your simulation, it's identical to a parallel 2D cut. And so what you do is it allows you to simplify the 3D problem, but still capture a lot more of the physics than a standard 2D. Okay, so an example of creating this 2.5D is thinking of a cylinder, which is an infinitely long cylinder and its axial symmetry in the simplest case. And some of the best known solutions, a simple case, is what I was kind of alluding to right at the beginning of what a flux rope is, and that's created through Bessel functions, and it's known as a Lundquist solution is one of the first. So in terms of creating an analytical solution in 3D of a flux rope, there are two main models, two main attempts. One's called the Gibson-Low, and the other is the Titov-Demoulin. And what they're doing is they're creating a 3D analytical solution in maths of all these field lines and how they twist. And it's a full mathematical solution to this that can be introduced as equations, as it were, into a simulation that creates your flux rope. And they're slightly different solutions, and they have slightly different benefits and weaknesses. This is one example I pulled out just to highlight what these simulations are capable of doing. But as an example, this is a Titov-Demoulin flux rope. And in order, what the researchers found, Ilya Rusev found, was actually in order to get this flux rope to escape and to erupt, it was actually necessary to modify the configuration by eliminating the arcade field. And so the arcade field is what I was saying, which is an arcade that goes over this polarity inversion line. But it's effectively field line that's above this CME that's trapping it and holding it down. And so in order to get this CME to erupt, he had to remove this field that's overlying it so that it would actually erupt. So this is part of the problem of ignoring the initiation problem. If you don't really have a solid handle, you have to start creating artificial methodologies to get your eruption. And so that's what many of these do, and many of the teams that look at both of these models will have some methodology of erupting it, and they will do something unphysical. So it's important to understand the assumptions and talk to the researchers and read the papers to understand what they've done to make it so pretty and look identical to the observations. This I just pulled out from Gibson-Low's paper to show the actual flux rope itself of what the mathematics provide. And I wanted to show this rather than the equations because the equations are pages of maths in an appendix and unnecessary for you guys to go through in detail unless this is a particular area of research you're doing. What you really want to take away is what is the conceptual picture of the CME. And so what they've got is this is the blue and the yellow are the field lines of the actual analytical solution. And you're seeing this, and there's a set of solutions that you can get from these equations. And this is one of them. And what it's showing is how it looks and how it behaves if they change the equations and change the heights of the CME. So going into a bit more details of the Gibson-Low, and using those equations into an MHD simulation, they try to get an idea of how well does it work. And what some of the initial papers were showing was that they find that excessive acceleration is resulted from this Gibson-Low solution. Essentially, this is because it has a high beta equilibrium state. And placing it into a realistic coronal environment necessarily places it into a low beta regime. The other thing was simulation begins with a state of force imbalance, and that's due to the removal of part of the plasma in the flux rope, and is also from insufficient background of the coronal plasma pressure to offset the magnetic pressure of the flux rope. So that's the same idea as you're trying to destabilize it by just removing fields in different locations so that you can get this thing to erupt. And it's this idea that you have this force imbalance that creates this acceleration. And in this case, and this is the important part, is the force imbalance produces an acceleration that is actually too large to be correct. But for some reason, it ultimately yielded appropriate amounts of energy, which then made it look similar to observations. And for these reasons of acceleration, this model, in this case, it was shown to be suitable for modeling for the declining phase of an impulsive event. So they're not trying to do the initiation problem, but once you assume that, once you look at observations and you say it's already initiated, and the CME is now beginning to propagate into the heliosphere, this model and the simulation is somewhat appropriate. So the other version of the model is the Titov-Demoulin Flux Ro. And their motivation for this approach was to achieve, is that the solar active regions may be thought of as composed of such flux tubes. The method allows to study a sequence of force-free configurations through which the flux tubes emerges. And so in this mathematical set of equations, the three things you want to kind of take away is that they have three field sources for which they create their flux rope structure. One is the twisted flux rope itself. The other they create through magnetic charges, there's sort of these hypothetical magnetic charges that they have, which will create a magnetic field. And third, a line current that they create. And this fully describes how they're behaving or creating this flux rope. And the further details go into describing exactly how they set up this flux rope. Again, so I've just gone into a lot more details here for you guys to have, so that you have a handle on exactly what's going on with the Titov-Demoulin Flux Ro. And so I mentioned here two opposite magnetic monopoles of strength Q are placed on the axis separated by the distance L. These monopoles are responsible for the poloidal potential field. This field has its field lines overlying the force-free current and stabilizes the otherwise unstable configuration. And so this is all about how they try to stabilize and unstabilize certain characteristics. And depending on the choices of the parameters, one can contain a stable or an unstable nonlinear force-free configuration. And so there's basically a set of equations for this flux rope. And some of them are naturally stable and some of them are naturally unstable. And this particular simulation that was created was done to replicate an observation that was seen. And the set of equations used for this naturally came out from an unstable branch of the set of equations that the Titov-Demoulin provide. And so you'll get certain situations when you want to use different solutions. And no doubt, Torok used many different simulations with many different sets of equations, tried to get something that replicated this scenario. Then I just wanted to go quickly into some other analytical solutions. And I didn't want to dwell on them too much, but I wanted you to be aware that they exist. And so you've got the Jimmy Chen's model who also described a flux rate from the photosphere, from the surface, and tried to describe how a set of equations that would solve this. So while this solution is actually entirely 3D, it can pretty much be all this pre-described. The entire structure can be pre-described by one parameter, which is effectively the height of the CME. And so you can set up the entire 3D structure by, in effect, mostly just tweaking one parameter, which is the height. There's another solution that's coming out in publication now, which is done by Nieves Chinchilla, and she's actually created it from a heliospheric point of view. So she looked at it from space and looked at all the solutions using time series of in situ data and try to create a mathematical solution that allows for many different current densities occurring. So that allows you to describe lots of the evolutionary effects. But she has a solution that is very general, which may in the future provide a new analytical model that can be used in simulations. But in that case, it's watch this space for that. So now we have a rough idea of the initiation problem, looking at sort of simulations into the heliosphere that we've got lots of models for how they can initiate. We've got a few different models of how they try to replicate what they see in observations. What I want to move on to is the actual observations that we actually have, and what kind of properties they have, and what we can actually measure. And a lot of this is in the same as the top two sections. Is an idea is I just want you guys to have lots of tools to hand to have an understanding of what is possible. And so if you ever want to talk to other scientists outside your field, you want to have an idea of what is possible to measure and what is possible to corroborate. And so there are a larger variety of different things that we can measure with CMEs. And I come from it not from an actual point of view of what instruments we can use, but what are the actual fundamental characteristics of the CMEs. And so the idea is you will want to look at many different data sets as possible from many different instruments and different teams. But these are the characteristics which are pretty much what we can actually measure right now, and which is the speed, the amount of flux inside the CME, the magnetic field of the CME, their mass and therefore density. And in fact, we're trying to get an idea of what their shock geometry is. And so I'm going to go through lots of different methodologies people have tried to do, trying to answer how we can actually get these values from observations. And so firstly, I'm just going to talk, if you guys want to do statistical work on trying to get an idea of how these characteristics of CMEs, of how fast they go with solar cycle perhaps, or what is the general average in different areas, there's lots of different catalogs, databases from which you can scrape data quickly and so that you can get general handle of data sets. But if you're using a lot of these data sets, I should point out some of these are automated, some are semi-automated, and some are model. There's a semi-automated one that's coming out by John Hopkins, being led by Angelos Voulidis, where it's a kind of a mix between automating certain characters, manually selecting the initial characteristics and letting algorithms calculate the rest. But in both cases, if you're going to start using trying to create lots of insights with these catalogs, you want to ask the developers of these algorithms of if it's possible to do what you think you want to do. And that's because there's lots of strengths and weaknesses, both with manual and and the automated. And here's an example of why you want to be careful of how to use large catalogs of CMEs without understanding the algorithm of what created these automatic detections. And this is an example I just want to quickly highlight, is an idea that people were talking about solar cycle 24 being quiet and not having so many CMEs and being unusual. And you probably would have heard this in general literature or other scientists talking about it. But if you look at the catalogs, they actually show that the monthly CME rate is somewhat no different to what happened in solar cycle 23. And this caused a lot of confusion and people were wondering what's going on. But once you get under the hood of what's going on, an example of this particular catalog, and this is CDOR, and this is done by manually measuring all the CMEs. Here, what has been found, and not necessarily written in the papers, is that at this point here in 2006, the actual cadence of the images, the number of images per minute that were taken by the coronagraphs increased dramatically. And because of that, when the scientists manually went into looking at these images, and if you have a trained eye that spends hours just flicking backwards and forwards over sets of images, you are capable of seeing very faint objects. And if you have higher cadence, you're able to see the more faint objects. And so what happened was, you see at this point, okay, so let me look at it here. This will be easier. Okay, so what you're seeing here is this red line here is the cadence of your images. And so what you're seeing is a bump happening in 2010 of when you're getting much more images. And so what they did was, if you have if you look at the total number of CMEs over the solar cycle, which is this blue-black line, I've covered it up a bit, but it goes really high during that period. But what you're also noticing is that you're getting an increase in the number of poor events, which is described as events which are these very faint and wispy type CMEs. And so what people wouldn't necessarily call CMEs, or what I should describe it as the opposite of what I've been showing you so far, which is your nice big structure of a CME. There are things which are just minor and not worthy of showing in presentations hardly. But these things get captured as being a CME. And so it's the correlation between these two that you want to be wary of. So in summary, in this scenario, it's been shown that the increase of CME detections in these catalogs are often actually down to a higher cadence of the images, which then led to a higher rate of CMEs, both in the automatic catalog and the manual catalogs. And once you've removed all these poor events, then things stabilize and you get something which is more what we're thinking in this case, in this catalog, which is once you've removed the poor events, you actually show that the CME rate is decreased in this solar cycle. This is, I wanted to show some basic parameters from CMEs that have been pulled from these catalogs. And this was done pre sort of the latest data of solar cycle 24, and so without that complexity. And this was done by Yashiro, who's one of the guys that creates the CDOR manual catalog. And so once you take these catalogs, I mean, what can you do with them? And so some of the simplest things is to have a look at how fast they're leaving the coronagraphs, so you get an idea of velocity, and also how wide they are. You know, are they halo events or are they very narrow events? And so you can pull out lots of insights into how these objects, CMEs, evolve over the solar cycle and what their general averages are. And what you notice is that there are differences during different solar cycles and different years, and there are different characteristics between slow CMEs and fast CMEs. And these are important if you want to ever make assumptions of what a CME is. If you are a magnetospheric physicist, for example, and you want to have a handle on what kind of CME you should inject as a typical CME, you want to be wary of where you are in the solar cycle, as well as what kind of events you want to look at. Going quickly back to the solar surface, what is some of the characteristics in terms of solar cycle variations do we notice? And this is something that will start coming up, that people will start talking about a lot more in the next few years, as people are trying to predict the magnetic field of CMEs for forecasting purposes. And this is an idea that is driven by something that Volker Bothmer kind of alluded to back in 1998. And what he was suggesting is that back then is that CME should have a magnetic characteristic that is somewhat predictable, and it should be driven by the underlying solar dynamo theory. And what he was suggesting is if you've got the solar dynamo doing changes that happen on a much more macroscopic scale, then you have, depending on which solar cycle you're in, you're going to have these active regions which should be consistent throughout the solar cycle. And this is predominantly true. And so in even solar cycles, so solar cycle 24 like we're in now, odd solar cycles like the previous solar cycle, 23, what you'll see is in the northern hemisphere, you'll have an active region where it will be leading with a positive polarity. And in the southern hemisphere, you'll have something that will be leading with a negative polarity. And that's pretty consistent, and you'll see that with the butterfly effects. And the opposite happens with even solar cycles. It's in the northern hemisphere, it'll be leading with a negative edge. And if you believe these characteristics, then that should mean it's somewhat predictable to have an idea of how the field line arcades should behave, because you know field lines should go from the positive to the negative, and they should be going in one direction. And if you know what the direction of the active regions are, you should have a handle on what the kind of magnetic structure of the CME should be. And if that's true, then we should be able to have an idea of predicting CMEs. And so what he was arguing was that actually just down through some basic sort of dynamo theory, in effect, there should be four main characteristics of CMEs in what she describes as southeast-west, southwest-north, all these different characteristics, but four general structures. And everything should modify from that. And what I'll talk about a little bit in terms of space weather forecasting at the end of tomorrow, the second lecture, is how we have to modify that, because there's even more complexities. But this is what I wanted you to walk away from here is a general idea that there is a concept of being able to understand that CMEs have somewhat predictable general characteristics driven by their active region's polarity. So, moving through our different characteristics that we're going to try to show through observations, I'm going to go through all the different topics and properties, and we'll start with CME, speed. And so with speed, the general kind of characteristics what I was kind of showing before is usually around the sort of 600-700 kilometers a second, but you can get very extreme events. And under extreme events, as it's not unheard of to see things between the 2,000 and 3,000 kilometers a second scale. Now, those are very rarely seen, but those are the working theories of the somewhat maximum speeds that CMEs can have. And with the majority of them occurring between your 400s to 1,000 kilometers a second. And looking at the CDOR catalog, and if you go into the catalog, you guys have been working quite a lot with the tutorials and stuff, and so you seem quite adept at being able to use these things. And if you go into the CDOR catalog, you can click on some of the links, and you'll get profiles of how these CMEs move in the inner heliosphere, so before 30, 40 solar radii. And what's important with this is that the slow CMEs, they tend to have an acceleration profile, and so they go out and accelerate. Whereas those that initiate at a very explosive high speed, they tend to get held back by the solar wind ahead of it, and they decelerate and go. And so the idea is, in both of these scenarios, CMEs tend to accelerate if they start off with a speed below the solar wind. They accelerate if they go below the solar wind speed, and if their initial speeds are higher than the solar wind, they tend to decelerate. So the idea is they end up trying to get back to the solar wind speed. CME flux content. Oh, okay, I skipped over that. But actually, this I'm going to go into briefly because this is important for context for the flare lecture. And so the idea here is, and I've drawn it very small, and I apologize for that, but the schematic of what we're talking about of a CME and the reconnection is this being the CME here, and this is the flaring arcade. And I did a really bad schematic that has no current sheet, so I apologize for that. But the idea here is what happens as you get reconnection below the flux rope. So this is the flux rope that's being created. If you get reconnection occurring below, you get, there is an amount of flux that is now contained in the flux rope. And that flux is also identical to the flux that's in the arcade itself that's below, because they were the same field lines. So if you get reconnection, if you want to know what the flux is in the CME, you can look and go, well, it's a proxy to the flux that's in these loops. And these loops, when you get flaring, you get energetic particles that are coming down to this photosphere, and you create these. If you imagine this arcade as 3D, like that cylinder I was showing, you get these arcades, and on the photosphere, there'll be these things called flare ribbons. And these flare ribbons, what I'm showing here is yellow. And so if you know this is the flux that is also in the CME, you can measure the amount of flux that's coming out of the photosphere in the flare ribbons, and you can use that as a proxy. And so what's happening here, if you go through, is what I'm showing here is, sorry, I should have done this the right way. So the flux contained in both the top section and the bottom section of the reconnection are the same. And that can be measured by the flare brightenings. And so as time moves on, the flux of the outer loops of the CME reconnect, and so you get different parts. And also that means the locations of the flare ribbons change over time. And so you first can go to look at observations of the solar disk, and you see where the flare ribbons are, and you can overlay magnetograms, and you can find out what the flux is at those points. And then at a later point in time when the flare ribbons have moved, you can work out what the flux is under those ribbons. And you can work out over successive images the amount of flux that's being added into the CME by looking at the amount of flux that's coming from the flare ribbons. So that's a concept that was looked at before, and I should have had a paper. The paper, okay, for some reason, the paper was done by Chu in 2006 that first looked at it, and they've done a few papers after. For some reason, I've the accreditation to the scientists is missing, so I apologize. Okay. Then another big question, actually, and this is quite a hot topic at the moment, is trying to estimate the magnetic field. Sorry. All right. So yes, I didn't mention it's not the total flux and it's not the toroidal flux. So what you're questioning is, so I should have been explicit when I spoke it, but the flux that you measure in the flare ribbons is equivalent to the poloidal flux of the CME, not the toroidal flux. Is that answering your question? Oh, okay, sorry. Okay, my fault. Okay, this is your flux rope, okay, a big cylinder. The toroidal flux is the thing that's going through the center of this cylinder. And the poloidal flux is the thing that's wrapping around this object. And so in this diagram, what you're seeing is the end on the circle, okay? So you're not seeing the depth of this, which is here. But it's the twist this way, the poloidal, which is what you're measuring in the flare ribbons, which are tracked like this. Does that help? Okay. Okay. Moving on. So what I was saying with the magnetic field, this is quite a hot topic right now. People are looking at, in the bigger picture of space weather forecasting, and they're looking at how the magnetic field can be predicted at L1, and therefore give you lead time of how to estimate the magnetic field for space weather. And so there are a few different strategies, actually, and I'm going to just quickly, briefly try to allude to a few that people are trying to test. And so these are different strategies that people are trying, and again, strengths and weaknesses and many assumptions in all of them. And one of the strategies is a paper done by Sam Turn, is looking at how we can estimate the magnetic field inside a CME. And he looks at using type 4 radio bursts to do this. I've again skipped over both now and latest lecture radio bursts or radio data. And there's a great lecture done by Marabisi in years past that went into all the details of radio data. And that's all on the summer school. So I'd invite you to go see that if you want details of radio data. But here, what he's done is he's looked at radio data and the type 4 moving radio burst, and he tried to create the magnetic field strength in the core of the CME itself, which is different to many other strategies that are looking at the magnetic field at slightly different areas of the CME. But this is the first that I found of trying to find out the actual CME magnetic field in the core itself. And what he does is he can use the radio data, make some assumptions of what the volume of this is, of this core of the CME is. Once you know the volume of it, then you can make estimates of the magnetic field strength. And a methodology for looking at the volume will be talked about later in this afternoon's lecture, and that's about triangulating CMEs. And it's a methodology by using lots of cameras at different points in the heliosphere to get a handle, and we'll go into that in more detail later. CME mass, that's an intriguing one, and I'm running out of somewhat time, so I'm going to go through this quickly. What we have in coronagraphs is white light images. And what that actually means is what we're seeing is electrons from a process called Thomson scattering. And if you know how bright your pixel is, and you know some theory about Thomson scattering, you can make an assumption of how many electrons are all along that column between you and to infinity that follows that pixel. So you get an understanding of that. And so what you do is you make an assumption, several assumptions of converting the amount of total brightness into a number of total electrons. And then you make assumptions that it's all happening on the plane of sky because that's where the maximum amount of scattering is happening, which is predominantly okay, but you get somewhat some large assumptions and some large uncertainties. And we're going to skip over the exact detailing, but a lot of this is in SolarSoft of how to convert white light images into mass images. Again, if you want to go into actually doing this yourself and get under the hood, come speak to me afterwards. And the basic process is lots of algorithms in SolarSoft which will do it. And that allows you to look at these white light images, convert them into mass, and so effectively you have an image like this, which is now a mass image. So every pixel actually is a value of the amount of mass in that pixel, not the amount of light. And then you can add up all these pixels, much like light, and get an estimate of the total amount of mass. And so you can do interesting things, like you can look at an entire sector, get an idea of what its entire CME mass is, and see how that mass changes as it evolves into the heliosphere. You can do things like what we saw earlier, which is just the core region, and you can pick out certain elements, which is intriguing. Or just, let's say, the shock and sheath region, and you want to have an idea of how that works. Or something I did a few years ago, which is this, which is looking at the bigger picture. Okay, so I won't go into that. I'll just leave it as a static, and you can believe me, it's similar to other images where the CME is coming out, and it goes over this blue box. And I've chosen this blue box to remain static, and what I did was looked at the mass at that blue box for each frame. And so then you can do something intriguing, which is you can create a time series of mass over this box. And that box happens to be at the same location for radial propagation that will take you to Earth. And so you can create a time series of mass, which you can make assumptions of will be at Earth. If you have an idea of what the volume of this CME is, you can then convert your mass into a density, and you can do intriguing things like create a time series of what your density of your CME should be at Earth as a methodology of seeing if that helps with forecasting. So moving on to shock geometry. Lots of interesting things to be done with this, in particular when you can triangulate. And so you need to be able to look at CMEs from different perspectives, not just at Earth. And that gives you an ability to get an idea of its full 3D structure. But a few years ago, it's not been, it's now commonly accepted that you can see shocks, or rather the compressed plasma behind the shock in these coronographic images, but it wasn't initially well accepted. And this is, again, about being adept at manipulating images. So you have coronographic images, and often you see, especially if you go in through the ISO system and you just look at the JPEGs, you'll see the CMEs. But if you go into the FITS files, the raw data, you can change the color scaling, and you can highlight and pick out, you can basically oversaturate the CME, and because you don't care about that. But then you can pick out other highlights and intensities, which are actually the shock sheath region. And in this case, this was the first paper that was published by Veludis, trying to prove that point. And what he's saying is he's oversaturated the CME itself, and that's what you normally would have seen. But once you do that, you have this other dome, which is intriguing, and you go, what is that? And you can see that evolving and being driven effectively by the CME. And his theory that it was effectively the shock. In fact, like we say, you're not going to see the shock, you're going to see the compressed plasma behind it, but it's effectively, for all intents and purposes, the line of where the shock should be. And there's been many papers that have then moved on with this and have highlighted this at much better image processing. And this is another example where this is the standard CME. And once you change the color scaling, you can see this very brief, very light region over here. And once you've done that, you can see this. And what you see, if you did it as a movie, is that this little section here gets deflected. And if you had not changed the color scaling, you would have seen this object deflect, but you would have had no reason why. But once you can change the scaling and you show that the shock is actually approaching this region here, and you have a handle of why it's been deflected. Again, this was a slide I wanted to include. I put it into the shock geometry, but it's actually to do with magnetic field, what I was showing earlier. This is intriguing because, and I'll go into this later as well, but he's looking at the shock standoff distance. And the shock standoff distance is basically the distance between where you think the shock is and the distance to where the flux rep is, or the CME is, and that's the sheath width. And that shock standoff distance, you can correlate when you make some assumptions, well, a bunch of assumptions, and the geometry. You can then try to pull out what the magnetic field should be upstream of the shock, which seems very intriguing. And this has been done at several heliospheric distances to see if there's a way of estimating the magnetic field in the low corona and the heliosphere. And so this is done using SDO, and you can get estimates of what the magnetic field should be that low down, as well as using cameras that are looking into the heliosphere, the stereo data, and making assumptions of what it is out here as well. Now, I didn't show it in this figure, but there's other papers that have now come out where effectively it's like out here, which is about 30 to 50 solar radii. So I'm going to finish off now. Well, I'm running a bit late, sorry. I'll finish off quickly on CMEs, but on different astrospheres. And we're kind of alluding to some that we had some talks about that earlier in terms of what its effect is on different astrospheres. And so what I wanted to get an idea of is, with these concepts, we can theorize how CMEs can have drastically different consequences at different stars, because they can have, because many of these stars can be at different places on the main sequence of the Hertzsprung-Russell diagram. And so, as an example for young active stars, younger stars can have active regions that occur at higher latitudes. And if that's true, then we can expect a significantly different distribution of CMEs in their atmosphere. So you're likely to have CMEs that occur at higher latitudes or at the poles, which would be intriguing. Also, if the star is rotating much faster, that will create a buildup of magnetic energy, which will have a different distribution, and that can potentially trigger much larger flares, which can then lead to much larger CMEs. And that'll give you a different threshold for what you consider extreme events. So if you're looking into extreme properties of CMEs, while that might be true for our solar system, that will not necessarily be true for other solar systems. The rate of CME release can vary, therefore, with solar cycle. It varies with our solar cycle. It is therefore fair to say that it will vary for other astrospheres. And so if you have a different rate of CME release, then you have a different amount of magnetic flux that's being added into the interplanetary medium. I say interplanetary, it's astrospheric magnetic field. And so then you have a greater variability from solar maximum to solar minimum. And so that's sort of talking about how the different astropheres and how you can potentially get different characteristics that are seen outside our solar system. And then the bigger question for that is then leading to what is considered the habitable zone in those cases. And so I'd invite you to read into the chapter in the fourth book that you guys have got, into looking into how CMEs can affect what is and is not the habitable zone. Okay. So I'm going to sort of end there, and we'll kind of skip over if that's okay. Thank you. Any questions? Or you want to talk to me later? Break time? Yeah. Right. Right, okay. So the question for those that couldn't hear is I briefly alluded to the idea of the three-part structure of a CME. And he was saying we have observations that don't have the three parts. And that's what I was trying to allude to before, was that was a question of great debate pre-stereo, was that you have three-part structures, and then people go, well, I see CMEs that don't have the three-part. Does that mean this three-part means nothing, or is it a specific case study? And once you can look at CMEs at different points in the heliosphere, so using the stereo at different points, what you find is a lot of it is a projection effect. So many of these things is, if you see a CME and it does not have a three-part structure, if you move to somewhere else in the heliosphere, you probably do see the three-part structure. So that certainly removes many of the events. But you know, the world is not so uniform. And so you'll still see events that don't have this classic structure. And that is true. And again, but most of it is, the way to describe it is, in the three-part structure, that core section is considered the prominence. And that is the part that is under debate that people talk about, and is, do all CMEs have prominences or not? And where should that be? Should it be in the center? Should it be further up? And whatnot. So your question is, if it's spindly or not, that's really often to say where that prominence section is. So I think that's how I'd answer that. In terms of being very narrow, that's just a question of different type of CMEs, and having its trigger mechanism being slightly different. And so then I would argue that would be a different case, and I would say that's not something you'd want to label under the same banner. Any more? Okay. I think that's it. Shall I leave it to you, Nick?